We're now going to use a simple model to try to derive the energies for the simplest possible molecule. And this simplest possible molecule is the hydrogen molecule ion. So we've got one nucleus here with one proton, nucleus A, one nucleus here with another proton, nucleus B, and there's only one electron, so this is H2+. And we have three distances to be concerned about: RA, distance from electron to nucleus A; RB, same thing to nucleus B; and RAB, the distance between the nuclei. So our Hamiltonian for this system consists of four terms. There's only one kinetic energy term because of the Born-Oppenheimer approximation. The nuclei are fixed, so they have no kinetic energy. The electron has its kinetic energy in atomic units, -1/2 del squared. Our wave function is a function of the coordinates of the electron. And we have its attraction to nucleus A, its attraction to nucleus B, and the repulsion of the two nuclei from each other. So these are the terms that are going to play off of each other. Our wave function is going to be a combination of two basis functions, and we're going to have psi A, which is the 1s orbital centered at nucleus A, and psi B, the 1s orbital centered at nucleus B. And our trial wave function is going to be some linear combination of these two basis functions here. So in terms of their functional form, that's a normalization constant times e to the minus r minus ra and r minus rb, centered at nucleus A and nucleus B. So in the linear variational method, we have the matrix equation for our Hamiltonian. We have two basis functions, so this is a 2x2 Hamiltonian matrix. The Hamiltonian matrix H acts on the coefficient vector for CA and CB, a two-element vector. H acting on C equals the energy times C. That's an matrix eigenvalue equation. And we have find the solutions for energy by setting the determinant of H minus E times what we call the overlap matrix S, how well these functions overlap with each other, and that has to equal 0. Okay, so we'll get started with this example, see how this is going to work. So for our specific case, we have HAA minus ESAA for the first element of this H minus ES determinant. Then we have HAB minus E overlap of A and B. Then we have in the second row HBA minus ESBA, HBB minus ESBB. And that's going to be equal to 0. But we can also make several other simplifications. So this integral here, these H and S integrals, are just the integral of psi star A, H psi A, the Hamiltonian, psi star B, H psi B, etc. And then these overlap elements are just the integral of psi star A, psi B, psi star B, psi A, etc. So we actually can make some simplifications. In terms of the Hamiltonian, the matrix elements HAA and HBB are equal to one another. So that simplifies because how the electron interacts with each nucleus is going to be completely equivalent. Then we have HAB equals HBA because our wave function is real. So the integral of psi star A H psi B is going to be the same as psi star B H psi A. And we also know that since this wave function is normalized, with this normalization constant here, our SAA and SBB are both going to be equal to 1 because this wave function is normalized here. Integral of psi star A psi A is going to be 1. And of course the overlap SAB equals SBA. Okay, so with that in mind, what our determinant simplifies down to is HAA minus E. This is now 1. HAB minus E SAB. And then this element on the lower diagonal here is the same. And we have the same. So the terms across from each other are now the same, and this all equals 0 as we set up there. So expanding that out, you get the following expression. You're going to have HAA minus E squared plus HAB minus ESAB squared equals 0, because you're going to have this times this minus this times this. That's how you do a 2 by 2 determinant. So when you solve that, you end up getting two solutions because of the square here when you solve for E. You should be able to convince yourself that the algebraic final result for our two states is going to be HAA plus or minus HAB over 1 plus or minus SAB. Okay, so these are energy expressions. We have kind of the Hamiltonian matrix element for how our electron interacts with one nucleus there, plus or minus this coupling term, how well it kind of interacts between these two wave functions on each of these nuclei here, and then over 1 plus the overlap of these two wave functions as a function of their separation. Okay, so let's look in some more detail at what these Hamiltonian matrix elements come out to look like. Okay, so for HAA, this Hamiltonian is a linear operator. All of these operators can be separated out by themselves. So we're going to have psi A, integral of psi A, minus 1/2 del squared, again atomic units, psi A. So that's an integral of psi star A minus 1/2 del squared psi A, integral over the entire domain of the wave function, which is just the 3 spatial coordinates of electron 1. We have a 3-dimensional wave function, plus next term in the Hamiltonian, psi A minus 1 over RA, psi A, plus our next term involves the interaction of an electron in basis function A with nucleus B, and then plus our final term, which is going to be psi A 1 over RAB psi A. Okay, so there are immediate simplifications we can make. This RAB doesn't have electronic coordinates in it, so it just factors out this. Then we have psi star A psi A integral, and that's 1 because this is normalized. So this simplifies to just becoming 1 over RAB. The repulsion of our nuclei is not affected by what the shape of the electron of this electron's wave function is. So that term is nice and algebraically simple. We know this integral from the hydrogen atom. This is an atomic unit, so I'm just going to go ahead and spoil that this is plus 1/2 in Hartrees. That's the unit we're working in, atomic units. The attraction of the electron to the nucleus when it is in psi star A psi A, so its density is all at nucleus A for this element, HAA. That's just the potential energy for the electron in the hydrogen atom, and that is minus 1/2. Okay, then we're left with this final term, which is the charge density of an electron in psi A, so psi star A psi A, and how that is attracted to nucleus B. And that is going to be a somewhat more complicated functional form that we're going to define on the next page, which we'll call JAB. We're going to define that as a function of R. So this is going to be the attraction of the charge density of an electron over nucleus A interacting with that nucleus B, and that's going to change depending on how far the nuclei are apart. Okay, then our second element that we need to worry about is going to be this HAB. Okay, and that's going to be integral psi star A. We have minus 1/2 del squared psi B. We're going to have the same 4 terms, but now instead of having psi A here, we're going to have psi B in the ket. psi A minus 1 over Ra psi B plus psi A minus 1 over Rb psi B plus psi A, and then we have, again, 1 over Rab psi B. Okay, so just like before, this term is not affected by the electron's wave function or its form. This is still just 1 over Rab. It's a simple algebraic quantity. Nuclei repel themselves equally no matter what the electronic wave function is. Okay, then in terms of these individual terms here, we're going to have a more complicated functional form. First of all, we have this kinetic energy operator for psi star A, then you have take the second derivative of psi B, multiply times minus 1/2. When this all shakes out, you get this somewhat complicated form, which is positive 1/2 e to the minus Rab, and then you have, open parentheses, 1 plus Rab minus R squared AB over 3. And there are going to be some fairly complicated functional forms like this. Don't worry about it too much. The purpose of this isn't the numbers. The purpose is the trends and what kind of general ideas pop out. So don't stress about the specific values. They're just meant to be indicative of something. Okay, then we have for here our interaction of the charge density of psi star A times psi B, so kind of this overlap of the two, and how that interacts with each nucleus, nucleus A and nucleus B. And this is going to be a quantity which we'll also define on this page, which is going to be called KAB. And these two integrals are equivalent to each other. The overlap density between psi A and psi B is going to interact equally with nucleus A and nucleus B. It's going to be symmetric with respect to the middle of this molecule here. So this is also going to be KAB as a function of RAB. Okay, so let's go ahead and define some of these quantities, what they're going to be as a function of distance. So we have this overlap, this SAB. That's going to be a function of the distance between these nuclei. And that's going to be e to the minus R, AB, to separation of the nuclei, 1 plus RAB plus RAB over 3. Okay, that's, RAB squared over 3. All right, that's fair enough. We have JAB, which we defined over here for the interaction of this charge density with nucleus B. And that is going to be e to the minus 2 RAB, when you do that integral, times 1 plus 1 over RAB, and then minus outside of the parentheses 1 over RAB. So that's how the charge density of psi star A, psi A interacts with nucleus B as a function of distance. We have this KAB, which is going to be involved in these terms here. And this is minus e to the minus RAB times the quantity 1 plus RAB. And this is indicative of how the overlap density, psi star A, psi B, how that density interacts with nucleus A or nucleus B. That density that's hanging out here in the middle of this molecule there. Okay, so in terms of these three quantities that we have here, this overlap, this J, and this K, we want to write these matrix elements HAA, HAB, and SAB, so we can have an explicit form for our energy. So if we do that, we're going to have that HAA, summing up all of these terms here, if you sum up all four of these terms, it's going to be minus 1/2. That is the energy of a hydrogen atom by itself, plus JAB as a function of the internuclear separation. Okay, that's fair enough. Then we have HAB, and that, if we do the plug and chug between these terms up here and everything down here, you'll see you can actually express this term in terms of S and K. So I'm just going to go ahead and write the final result, which is 1/2 SAB plus KAB, also a function of R, plus, then we have S RAB over RAB. So you have the overlap divided by the separation of the nuclei there. Okay, so that leads to an explicit form for this energy here as a function of distance, but we're really not interested so much in the energy itself, but in the difference between this energy and the energy of two hydrogen atoms infinitely separated apart. Because what we're going to have here is we're going to take two hydrogen atoms which are infinitely separated, define that as our zero of energy, and then as we bring them closer, we want to see what the potential energy surface looks like as a function of how far they're separated. We want to see what that potential energy curve looks like. So the energy of a hydrogen atom, the energy of just one hydrogen atom, is just minus 1/2 there. So if we want the quantity delta E plus and minus, there's going to be a plus and a minus state here. That's going to be our E plus minus minus twice the energy of two hydrogen atoms, which are separated infinitely apart there. And this is going to give us something which has a form a little bit like this. We have JAB plus 1 over R. All of this over 1 plus or minus S. And then the second term, we have plus or minus, depending on the state, KAB, RAB. Then we have plus this term here, S of R over R. I'm going to omit the subscript so that fits on the page, divided by 1 plus or minus S of R. Again, I'm going to omit the subscripts just for space reasons. So we have an expression here which is explicitly numerical for what this total energy is as a function of the separation of these two nuclei here. So if we graph this, what does this end up looking like? Well, we'll show two things here. We'll show the components and then we'll show the final result. So we've got an energy going up on the y-axis, and we've got RAB going up, energy on the y-axis, RAB going up on the x-axis. Okay, so we're going to have a few terms that are going to go on here. We have 1 over RAB, which is going to come into play. So that goes up like that. We're going to have this term JAB, which kind of starts down low here, then goes up and reaches a maximum for JAB. And then we have this KAB plus SAB RAB over R. And that starts out nearly zero, becomes slightly attractive, and then repulsive very quickly. So this term is that K plus S over R. Alright, so these three sum up according to this in positive and negative ways, and what they end up giving you, our final result, is we have one state which becomes attractive, reaches some minimum, and then goes up, and this is our E plus as a function of distance. Then we have another state which is going to become repulsive at all distances, and this is E minus. So one thing we should notice here is we have an energy which starts at 0 at infinite separation. They attract each other as they come closer and closer and closer. They reach some minimum at some preferred distance, some preferred RAB, and then the energy goes up very, very quickly again. And then this R min here would be what our bond length would be. So in fact, this very, very simple model, just treating the simplest possible molecule of H2 plus as being two basis functions, the 1s orbital on each nucleus. We use the linear variational method with this trial wave function as a combination of these two. We get these energy expressions here, and then these give us a functional form whose lowest energy state, whose ground state, actually predicts the shape for a interatomic potential energy curve that we had posited way back during the harmonic oscillator videos, that a molecule should have such a shape for this potential energy surface like that. And it predicts that there should be some minimum energy distance, and that would be what we would know as a bond length. So out of this very basic model, we've seen several very useful things which pop up in terms of what we think should be true about the properties of molecules. So we're going to roll with this model, and this is approximate, so we would have to have a more and more sophisticated guess for what this wave function should be in order to get more and more accurate results. But even this very crude qualitative result has provided some very nice insights and some predictions for what the behavior of the potential energy surface of molecules should be.